Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all of you. Okay, for the test one questions, so we haven't decided yet on the complexity or the toughness of the questions. We discuss this among the lecturers tonight. Okay, but for your information, question for the magnetic circuit will be the series, okay, series magnetic circuit, which we have already regularly do examples and so on. Okay, just for your information also, for the magnetic circuits, there are also magnetic circuit that are connected in series parallel. Okay, so actually that one have been discussed, I think, in the video. So I think since it is not tested in the test, so I think is enough to just watch the videos. Okay, because because when the topic had been assessed in the test, so it will be not be tested in your final exam. Okay, so meaning that the circuit, magnetic circuit will be not be inside your final exam. So we have reduced the burden of the student to revise during the final exam. It only started by this semesters. Okay, so we are concentrating on to excel your test one. So your test one will be AC power calculation, AC power topic, which is more towards on the single phase. And the second question will be on the magnetic circuit. So this is actually a sample of previous test one, which is under code of SEEE2423, I think around year 2018. Okay, so so the question is, consider a circuit shown here. So you have 3 loads connected in parallel with a single voltage source, 240 volt RMS. And this circuit as shown here is actually a 50 hertz frequencies. And the condition for the load is this one. So load 1 is 1260 degrees ohm. So positive meaning that this is inductive. So how to know it is inductive or capacitive is actually depends on this angle, or if you can put in a rectangular form, so the values will be positive J. Okay. And then you have the load, second load here, which is given R and capacitor. So you need to convert into its equivalent reactance values. Okay. And load 3, it only consume Q. Okay, positive Q. There is no P. Okay. So meaning that this one got P and Q, load 1, P and positive Q. Load 2, based on this value of impedance, so it will have a P and also negative Q. And load 3 only got positive Q only. Okay, so that is what information that we can obtain from this question. So the question is, based on the all condition mentioned above for the circuit in figure Q2, so find the complex power at each element. Okay, so I have already did it okay on these questions. Okay, so to have this one, what we need to do is for me, I always have my load in polar form and also rectangular form. Okay, so polar form or rectangular form. So from here, I can see that I got positive J. So meaning that your load is inductive. And for load 2, it only gives me information about the resistor value and also the capacitor. So the capacitor you need to convert into reactance, which is XC, which is 1 over omega C. For inductor is XL, which is omega L. Okay, so please be noted on that. So 1 over omega C, so we will obtain this one is ohm. Okay, 15.9 ohm. Since this is actually capacitor, so your impedance should be in 15 minus J, 15.9 ohm. Okay, please be noted here. Minus because this is actually a capacitor. And load 3 consume 2 kilovar. Okay. So the first question, we to find the complex power the total complex power supplied by the source. Okay, so what you need to do is to obtain all the complex power of all the loads, load 1, load number 2, and also load number 3. So the information given here is the impedance values and also the voltage here. We know that since this is parallel, so meaning that the voltage across the load is actually all 240 volt RMS. Okay, so we use that information. So we know that the complex power is equals to VRMS multiplied with IRMS conjugate. Okay. So, or in other words, you can write down, you can rewrite I in terms of voltage and impedance. So I will rewrite like this. And VRMS multiplied with VRMS conjugate. So the angle will become 0. So only the magnitude will be available here. Okay. Over the Z conjugate. Okay. So I use this equation for to obtain the complex power for the loads. For example, for load number 1, okay, complex power S1. So this is the voltage across the load, which is 240 volt magnitude only, because, okay, magnitude only, square, over the conjugate of the impedance. The impedance is, if you recall, is positive, okay, 60 degrees. So when it is conjugated, so it will become negative 60 degrees. Okay, please be noted on this also. So by using calculator, so this is my complex numbers. Okay, complex power. Okay, 4800 with an angle of 60. So the unit is VA. Okay, that is the complex power for load 1. And the second one is the complex power for load number 2. So same. So the voltage over the impedance conjugate. So right now the impedance is negative, right? So when it is conjugated, so it becomes positive. So my complex power for load number 2 is 2635 angle negative 46.7 VA. While for the complex power load number 3, since it only consumes 2000 var, so meaning that I can just use that information. My complex power is J 2000, or in other words 2000 with an angle of 90 degrees VA. Okay, so this one no problem. Okay, complex power for load number 3, because it only consume Q, there is no P. Okay, so finally the complex power is of the circuit, which is must be equals to the summation of all complex power of the load. Okay, so I compute, so I sum up them, S1, S2, and also S3. So I will obtain my values is equal to 4208 plus J4240, or in polar form is 597445.2 degrees. So this is unit VA. if I draw the triangular, the power triangular. So this one is actually your P total. This one is your Q total. And this one is your your total apparent power. Okay. The magnitude of your complex power here. So the overall here is actually the complex power, but the magnitude of the complex power, which is 5974, is actually a representation of the apparent power. So this is your apparent power total, okay? Okay, and this one, the angle here is your cos 45.2 is your power factor. So from total complex power, you can obtain all. Okay, so as the S total is actually also represent your complex power that's supplied by the source, because in a circuit, okay, all power supplied must equals to all power absorbed. Okay, so the total power inside the circuit must equals to the total power that has been supplied by the source. So your S total is also your S source. Okay, so meaning that if you are a designer, for example, you design a generator, what is the rating for electrical generator to power up these three loads? Okay, so based on the load requirement, okay, you need to have the complex power to be rated at these values, 5974 VA. So meaning that your generator should have a rating of 597. It can able to generate 5974 apparent power or VA. Okay, because P and Q is always changeable. Okay, it's always varied depending on the load demand and so on. But usually for the rating of the power generator, we always referring to the apparent power. Okay. Okay, so now, is there any questions? For the first one, it's straightforward. Okay, I hope you can understand the information given here. You can extract the information. Always know that your S is actually starting with VRMS multiplied with IRMS conjugate. Then from that, you can derive another equation from here, which is you have VRMS magnitude only over Z conjugate. Or you can also use IRMS magnitude only square multiply with Z. Okay. So actually these two equations derive from this one. Okay. Is there any question for the first one before we proceed for the second question? Second, third, and fourth is actually just straightforward. Okay, because we use information that we have already calculated from the first question. So as you can see here, the marks distribution is also quite small here because all the information has been calculated at the first questions. Okay, sometimes we don't know how to use the information, right? So that is why I try to do this and then discuss with you. Okay, so if there is no question, then we move to the second one. Find the current drawn from the source, meaning that what is the current here? Okay, since the voltage source is given, so meaning that you need to have here, and we have already calculated the total S, right? The total, what is the total power that has been supplied? Okay, the total apparent power. So we use that information. Okay, so the total power, the total complex power supplied by the source is 5974 52.2. sorry, 45.2. So it's equals to VRMS of the source multiply with the IRMS of the source conjugate. Okay. So we do this. Okay. So my current conjugate is 248945.2. And then we remove the conjugate. So this is your final answer. Okay. 24.89 negative 45.2 degrees amperes. Okay. Sometimes the student forgot this conjugate. Okay. So please be noted here. The conjugate is very important. Okay. So from here also, we know that since the current is negative 45 and the voltage is 0, we know that Vs is for 240 volt with an angle of 0 and the current is 24.89 negative 45. So if you plot the phasor, so this one is your voltage and this is your current. So your current is actually lagging the voltage. Okay, so this one 0, this one is 2045.2. So it's lagging. So you know when the current is lagging, so definitely you know that the total load is actually inductive. Okay. Okay. Straightforward. So and then the next is the what is the power factors. So the power factor, as you can see, is actually the cos of this angle, 45.2. So 0.705, but it didn't give information whether it is lagging or leading. So due to the information here from the current, we know that this current is lagging. So the power factor is actually 0.705 lagging. Next is this one, power factor correction. So find the value of the new capacitor such that the new power factor at the source is unity. So power factor is unity, meaning that to get 1, so meaning that your angle theta V minus theta I should be 0 degrees, meaning that the voltage and current are in phase. So right now, the voltage and current are lagging 45.2 degrees. So how can we make the current and voltage in phase together? Okay, so this angle is contributed because of the Q. Okay, if you have higher Q, meaning that your angle will be very, very high, so your power factor will become very low. Okay, so it is to obtain unity power factor, what you need to do is actually to make sure that the Q is 0. Okay, so right now, to obtain the power factor's unity, so you need to ensure that your Q is 0. So right now, your thought based on this calculation, okay, the complex power calculation, your Q due to this load is contributing 424 VAR. So in order to get Q is 0, so you need to install a capacitor parallel with the load also. And what is the Q? Okay. So since we want that to be power factor equal to unity, so your QC should also equals to the Q load. Okay, because the Q net should be Q load minus QC. So your QC should be 4240 also. Okay. Sorry, positive this one. Okay. So based on the equation, okay. So this is actually the equation. VRMS square over X conjugate. So it's equal to 4240. Okay. So your capacitor can, so The weight need to be installed should be 2.34 power of -4 farad. Okay, so when you install this capacitor value parallel with the load, you will have that your power factor will become unity. Okay, so this is actually the simplest technique on how to save your electrical bills. Okay, so you can try at home by inserting the capacitor. So you buy a capacitor, so and then you just slot in the positive and negative terminal of your socket. Then you will see that there is some reduction on electrical bills. Okay, is there any questions? I hope you understand this one. Okay. I will share uh, this solution to you after this, but I need to maybe to clean up this mess first. Any questions? So if there is no question, then we move to the second question. So on the magnetic circuit, series magnetic circuit. That one I think is quite good also because it quite uh it's not equals to what the example inside the slide. Okay, so sorry. Let me see where is the I cannot find my okay this one. Okay, I hope you can see this one, and I think you can download the questions from your our WhatsApp group. So right now, as you can see, examples in the slide I've already give you the length of the total length that of this materials. But now, usually in the test, we didn't give the total length of the materials. So the student need to calculate the lengths, the cross sections, and so on. Okay, so you need to maybe memorize the parameters equation for a circle and so on. Okay, parameters and so on. Okay, so this is a straightforward question actually, but the tricky is on to obtain the mean length, okay, the average length of this one. So the depth of the core is 10 centimeter. What is mean by the depth of the core is actually, this is actually a 3D. So meaning that you have a 3D, you imagine it is a 3D object here. So this is actually the length, it mean by depth. Okay, so 10 centimeter, the width of the object is a ferromagnetic core. So it is 10 centimeter. By assuming the magnetic leakage to be negligible and relative. Okay, so magnetic leakage. So I have already mentioned this in the videos, because when we have flux, okay, flowing inside this object, so there must be some losses. Okay, we call them as a magnetic leakage. So we assume that the magnetic leakage is 0. Okay, and the relative permeability of the core is 800, meaning that your mu r, okay, mu r is 800. So there is no unit because it is just a relative. Calculate the total reluctance and find the value of the current that will produce flux 0.01 Weber. Okay, so calculate the current. So meaning that what is the value of the current here that can produce flux 0.01 Weber inside this core. Okay, so the number of turn is given 500. So the circuit will be like this. So we have Ni, the number of turn multiplied with the current will be your source values. So since we have how many segment here? So we have maybe this 1, 2, 3, and 4 segment. So we have, I think, 4 resistor. Okay. So R1, R2, R3, and also R4. Why? Because we know that R is depending on the length over mu and cross section. So the cross section is actually not equals. It's not equal for each segment. So that's why we need to divide into 4 different resistor value. So right now, we need to calculate the length, the mean length of the first section. Okay, so this one from here to here, and then we have another section. Okay, so this is section 2, and then this is section 3, and then this is section 4. So it has been given the values of the length here, but this one is actually the mean, the average length. So section 1 is actually you compute from starting from here to here. So meaning that you have only 10 centimeter here, 40 centimeter, and another one is 5 centimeter. So your L1 should be 55 centimeter. Okay. And the cross section of the segment 1 here, So the cross section, I need to use another color. Okay. So this is the cross section. Okay. For segment 1. This is the segment 1. So the cross section is this. Okay. So we have the depth is 10 centimeter and the length of this one to this one is 30 centimeter. So your A1 should be 30 centimeter multiplied with 10 centimeter. So this one is 300 centimeter square, or in meter units is 300 multiplied 10 negative 4 meter square. Okay. This one also need to be converted into meter. So this one is 55 negative 2 meter. So all the units must be converted into meter and meter square. Okay. So you can right now calculate your R1. So your R1 is 55 negative 2 meter over your mu. So right now your mu must equals to mu R multiplied with mu O. Okay, so 800 multiplied with mu O from the calculator, constant 33. You just type constant 33. So mu O is actually the permeability of the what you call air. Okay, multiply with A1. So your A1 is 300 multiply negative 4 meter square. So you need to do that for every segment. Okay, every segment. For segment 2, this is actually your segment 2 here. Your cross section is this one. Okay, which is 10 multiplied with 10. Okay, 10 multiplied with 10. And for cross section number 3, this one, this section, the cross section is 30 multiplied with 10 centimeter square. Okay, so actually all the, I have already calculated it for you for your reference. So maybe you can refer to my solution here. So it is actually a straightforward, but sometimes I don't want you to make a silly mistake. Okay, for example, this one is sometimes I write down as a R or sometimes also S. It's actually referring to the same one, which is the resistance of the magnetic circuit. Okay, and then the total resistance. This is the total resistance. Okay, so not apparent power. So the total resistance is 126 kilo ohm. Okay, and we know that based on the circuit that we have drawn here, this is actually the flux. Okay, flux. So meaning that your flux is actually okay, so actually Ni is equals to flux multiply with the total of your resistance. Okay, total of your resistance. So from that, you can calculate your current, which is 2.5. So meaning that to create or to generate 0.01 Weber, you required current of 2.5 milliamperes. And lastly, the flux density, which is B at the top of the core. Okay, so actually meaning that it's actually inside the core actually. Okay, the overall core. So how to so the density is just you have the Weber, you have the flux total. Okay, at the top of the core. Sorry, at the top of the core meaning that this one only, the segment 1 only. Okay, segment 1 only. So it depends on the cross section. So you will obtain 0.3 Tesla. Okay. So I hope that one clear on that. So I will post this inside your WhatsApp group. Okay. So I think that's all from me. Is there anything that you want to ask before we dismiss our class? Uh, yes, yes. We normally write as the reluctance. Okay. It's actually no big deal actually if you write S or R. So the unit of the S total is okay, sorry. Not ohm, sorry. This is not ohm. Yeah, thank you very much. Because we just move from the question a single phase AC power. So this is not ohm. So this is actually a ampere turn per Weber. Yes, you are correct. Okay. Thank you very much. Okay, not ohms, okay? Okay. Okay, I think that's all.
Doctor,
Yeah.
do we get deducted mark if we don't put units?
No, no, no. It's
So
okay.
it's safer if we don't put unit
Yes, yes. Uh, on the important units that I hope you can get is actually Tesla and Weber.
Okay,
Uh,
noted.
okay, because the other parameter, for example, the reluctance is quite difficult to memorize, right? 80 over Weber. And then we have also parameters H, which is the strength. H is actually the strength of the field that created by the flux. Okay, so this one is also is actually Ni over L. Okay, which is the unit is ampere turn over meter. Okay, that is how we derive. Okay. Okay, I think not much formula need to be memorized. This one, but the what I call the density and then the strength, which is you can also use B is equal to mu H. Okay, or you can also get H is actually equals to Fi. Okay. But I think the complexity of the question is not very tough lah, because we consider online and so on. Okay, for the assignment, still I haven't get information about the assignment because we are what you call we are waiting for the person in charge to distribute to us. So when it is distributed, so I will give it to you directly. Okay. Actually by this week should be, but I don't know why it takes so long. Because we want to standardize all the assignments throughout the sections. For the test, no. The test will only series like this example. Okay, it might have what you call the air gap. Okay, the air gap. So meaning that you need to also calculate what is the reluctance of the air and also the reluctance of the core and so on. Some past year test one, I have already shared with you last week. You can refer to the WhatsApp group. Okay. That one I think the last year, I think last year ke last semester punya ni. How did the current got milliamperes? Huh? Based on the calculation, we got the milliamperes. What you mean by milliampere? Is it too small? Because of the value is too small? Or maybe the calculation is wrong? I haven't checked, but I think it is correct. Okay, so for example, if you have this, it depends on the question. So if the core materials is like this, okay, so where the cross section is not even, okay, the length is also not even, and so on. So you need, and then it give you the air gap here. So the total should be 5, including the air gap.
Doctor.
Yes.
When I calculated back the current, I got 2.52 ampere, not
Oh, is
milliamp.
it? Okay, okay. So meaning that maybe
Based
my
on
calculation. This
based
maybe
on
based on this
the
value. This
based
value
on
ke?
you that you write that yeah.
Okay, okay, okay. So maybe I miss itulah 165K multiply with, yeah, 2.25. Yeah, 2.25. No milli. Okay. 2.52 amperes. Okay. Thank you very much. But if the question give you the overall, for example, if you refer to the example in our slide, okay, it gives usually it give the total length, for example. The total length of the core material is 1 centimeter, for example, the total, meaning that the total, so it give you this one, this shape also, okay, but it give you the total length of this material is 1 meter, for example. So you don't need to calculate, okay, but if they give you this segment, this section, 20 centimeter, this section, so you need to calculate every section. So, okay, so I assume that this is the first section, this is second section, third section, and so on. Because as you can see, for the first and second section, the cross section is different. The cross section for section 1 is this big. But the second section, the cross section is actually this big. It's not equal. So that's why. So every section you need to calculate. Okay. For the third section, yes, the third section is this cross section. While the fourth section is, as you can see, this is 10 centimeter, this is 20 centimeter. So the cross section is different for sections. So actually the concept is actually you need to know the length and so on lah. Tak ada, I think no problem. Okay. If the section is actually all the same, then it's quite easy for you lah. But if, for example, this object, the cross section pun tak is actually not equals, the length is also not equal for each segment, then you need to do it in part by part. Okay, because the reluctance depends on the length of the section and the cross section of the section. If the dimension of the object is same for all section, then you just multiply with 4. Okay. So is there any questions? So if there is no question, then we can dismiss this class. Okay, what if I take R1? What if I take R1 70 centimeter? What do you mean? Oh, the length. R2 30 centimeter. So meaning that the length is 30 centimeter and so on. So why you... Oh, this one. Okay, so I understand your questions. So one of your friend asked me, what if I take the whole section from here to here, which is the total is 70 centimeter. It's not correct because you need to calculate the mean length. Okay, the mean length of the flux. So usually the flux will flow in the middle of the core. Okay, so we assume that the flux is actually will flow here. So the average. Okay, we calculate the average, which is from here the segment, this segment. Okay, so for the first segment, this is the segment of the flux flow. So 10, 40, and 5. Okay, 10, 40, and 5. Actually, the titik tengah lah, dia punya kata apa? The middle section, okay? The middle length. Okay. And for this section, the middle start from here, and then this is the whole length, and then till here. So actually the current flow here, current tak pergi ke ujung-ujung lah. Current is not flowing from this point to this point and so on. So we assume that the current is actually in the middle of the materials. How to know the length of the section of the air? For example, this one have no air gap. But if you, for example, this one, okay, your core is still this one. So this is your core. This is your solid core, okay? Which is, the shape is actually C. Okay, so I just draw back. So this is your air gap. So your air gap is 30 centimeter. So this is your length. This is your length of the air gap, 30 centimeter. Okay. Meaning that the others section is actually you start from here, section 1 to here. So this is number 1. Okay. And then section 2 here. This is section 2. And then this is section 3, the air gap. And then another one here. Section 3, section 4. And then another one, section 5. And then another one, section 6. So you have 6 sections, for example. Okay. So the cross section depends. So for example, the cross section for section number 1 is this. The cross section is this. Okay. 10 multiplied with 30. The cross section for section number 2. Okay. I need to draw. Okay. So the cross section is this one. 10 multiplied with 10. Okay. This is the cross section of section number 2. Section number 3, which is the air gap, is also 10. It's also this section also because it share the same cross section. Section number 4 also, the cross section is also same, 10 multiplied with 10. Section 5 is different. Section 5 yang ni lah, you refer to this punya cross section kan. Okay, and then for section number 6, this is your cross section. 20 multiplied with 10, dia punya depth dia tu. Okay. Oh, saya dah padam semua dah ni. Aduh. Saya tak payah save lah. Okay, so if there is no question, so you can refer to my YouTube video, the last section for this magnetic circuit. Okay. Next week we will go for transformers. Okay. So after this, it's up to you. So it's up to you to either to do this example by your own, and then you can watch my video after this. It's up to you. Maybe tonight or it's up to you. Okay, but by next week we will concentrate on the transformers, which is the topic number 2 in the subtopic inside this topic 2 magnetic. For source is unity, Q must be 0. Okay, so what you mean by the power factor? You mean the power factor of the source. If the power factor of the source is unity, meaning that the voltage and current of the source is in phase, yes, the Q will be 0. Okay, if you found out that the source and voltage, the source current and the voltage source is in phase, meaning that the power factor is unity, so they will not supply Q. But it's quite difficult lah, okay, because you are the source. The load sometimes requires Q because the Q have inductor, capacitor, so it's quite difficult that the source is actually only generating, supplying P kan. Okay, so usually the source has P and Q. So that's why when you design a power generator, you are referring to apparent power. Because okay, so you are not design the power generator based on the P. So I want to generate P. Okay, I want to generate P. I don't want to generate Q. That is not possible because your load is actually you have a numerous load. You have inductive, capacitive. So your generator should able to supply P and Q. So that's why the rating of the generator is always referring to the apparent power. Okay, so if there is no question, then we can dismiss this class. So I will upload this recorded video for the class. So meaning that you have 2 videos lah. Okay, the first one is these videos, and the last and the one is actually the video that I have pre-recorded for this magnetic circuit. Okay, so thank you very much. Assalamualaikum and have a good day.
Waalaikumsalam. Thank you, Doktor.
Okay.